have self-healing properties, such as bacterial-based self-healing concrete, materials that are enhanced, and I think Germain will touch on that in his presentations through adapted laboratory testing, etc. But certainly these are the two challenges that we are facing, is how to, in a sense, bridge the gap between the microstructures of the materials that we use and the asset that is delivered using these elementary materials. And the answer to that really is having data, information, and behavioral continuum across these different scales. And that is a huge challenge. I mean, we've spoken about BIM today, but BIM only addresses the asset level here. So this is where BIM is focused. But BIM is dependent on a number of components and materials that are at different scales of granularity. And it's very important to have the data information continuum to deliver the level of resilience that we need from our buildings. So this is where semantics come into play. I mean, BIM is one aspect of semantics. Again, BIM was developed originally as a data format, exchange format, but then it evolved gradually to be used to describe a building and its properties. But certainly semantics is a wider concept than BIM, and what we need is to be able to bridge the gap between the information silos that we have across these scales to deliver data and behavioral continuity across the four scales I've just mentioned. So the turning point from my perspective in my research was work I've done in the context of a FP7 project called WaterNet, where the project was coordinated by CSTB in France. Cardiff I was the technical coordinator. We worked with Intel. So we tried to address the problem of energy-water nexus, which was very interesting. As a result of this project, I mean, it was quite defining in the sense that we have published research in the Proceedings of the Royal Society, which is where Newton has published a few centuries ago his research. So it's quite an authoritative journals. But more important than that, we have established the foundation of what turned to be the way we develop digital twins. So as you can see on the screen, we tend to work around a semantic middleware where we try to source data, from different ways. We give context to the data, and then we use intelligence to make sense of the data and services to exploit the intelligence and make these available to a wide range of stakeholders. So we've progressed that and secured a patent in the US because you can't patent software in Europe. So we've recently secured a patent in the US, and that's what we're exploiting as part of the spin-out I've just mentioned to you. So let's get into more practical things. So I'll try to define what I mean or how I see a digital twin. So we have a helicopter view of Cardiff on the left side of the screen, a virtual view of Cardiff on the right side of the screen. So in a nutshell, a digital twin is a digital representation of a world, whatever that world is. It should be model-based, so it should be underpinned by semantics. BIM is an example of semantics, but we have GIS data. We have engineering analysis tools, and so on and so forth. It should convey a dynamic as opposed to a static reality. So for a city lives 24 hours a day, 7 days a week. It should be self-updatable through the sensors that sense the different aspects of the city. It should simulate and predict future outcomes. It should learn and adapt to unforeseen scenarios, including environmental and indoor changes. And most importantly, it should embrace complex socio-technical considerations. So digital twin is not only about technical aspect, but it should also be about social aspect, or it's a social technical development. So let's put things into context. So we live in a very complex urban landscape. So we see the proliferation of sensors wherever we go, in homes, on cars, in infrastructures, in buildings. So the problem we face right now is that it's very difficult because of the number of communication protocols that exist and other complexities. It's very difficult to make these network of sensors talk one to another, unless you do some retooling, etc., which is time-consuming and not seamlessly integrated. So the reason is that we're dealing with different terminology, we're dealing with different metadata, different meaning, different logic, and that's where we can see the advantage brought by semantics. I keep insisting on semantics. So semantics can enable really to sort out the terminology, the metadata, the meaning, and the logic of these network of sensors. And the way that we proceed is by sensing an environment. So once you sense the environment, thanks to the context, to the semantic, you can start processing the data you're getting from the environment. Once you process the data, then you can get some actionable insight. Again, depending on the scale of the work you're doing, it may be local insight or it may be global insight, as may be the case in a district or in a city level. So semantics play a key role in all this. Now, the issue we face then is, you see the number of sensors. I mean, someone mentioned the amount of data we get from these sensors. The challenge that we face then is how can we, in a real-time or near real-time basis, make sense of the data that we're getting from these sensors. So a human being can't cope with that. It's impossible. That's where AI comes into place. So artificial intelligence is very useful because it can interpret vast amounts of data, data lakes, I mean, in a very efficient way. But the issue we face then once we use AI is the one of, I mean, if you have to take decisions at a local level, for example, you can't afford the fact you may be facing with network latency or breakdown in communication. So that's where relying on edge computing, cloud edge computing, becomes an interesting solution in the sense that we decentralize the intelligence, some of it, or most of it, maybe on the cloud, but then we try and get it as close as possible to where that intelligence is needed, which is the edge. By applying that principle, so we can sense data, the data through the context can be processed in an intelligent way, then by using different, don't want to get into details, AI techniques, we can then hope to get what I insist on the word optimize, whereas before we're getting global insight, here we're getting optimized, actionable insights, which makes a clear difference between the scenario in which we were before. So just here, I want to insist also on the fact that the solution we've developed operates at different scales. We operate at a macro scale, which is a scale of a district or a city. We operate at a mesoscale, which is the one of a building, and I'll give you an example shortly. And we operate also at the micro scale, is when we enter a space in a building and want to really understand how that space is being used or how that space performs from an air quality as well as other perspectives. So let's take the example of the macro level. I'll start with the macro level. So this is work we did for the city of Cardiff. So we've been approached by the council. Cardiff, they manage over 350 buildings in the city centre. And the problem they have is they want to transition to net zero, but they have no control whatsoever on the various buildings they own. They don't know when they have been used. And so what we did is we developed a digital twin of the city. So then what we did is to try and understand what energy profile the different buildings they have by linking up to the smart meters, then trying to disaggregate the data and understand how the buildings behave. But certainly what we did then is we offered them a capability whereby if during term time a school is still heating up, whereas there's no one in the school, whereas before the school will carry on heating up or using the heating over the entire school duration, they could very quickly be notified that, hold on a second, it's holidays, and some of the spaces in your schools are warming up, the spaces. So that was quite an interesting and useful experience that we did with Cardiff City. Another example is in the case of Qatar. So we've worked closely with for the World Cup, that was a couple of years ago. And the issue that the organizing committee of the World Cup was kind of facing is the possibility of having a new variant COVID variant that may derail the entire organization of the World Cup. So what they've asked us to do is to look at, really have a multi-objective approach towards the problem of energy. They wanted to reduce energy, which wasn't, I can tell you, wasn't successful, but anyway. They wanted to reduce energy in their stadiums. They wanted also to ensure the comfort of the occupants, the people to come to stadiums. At the same time, they wanted to minimize the risk of COVID infections. So what we did, again, we developed a digital twin and we developed a simulation model, which we've calibrated using the data readings we got from the BMS. And the interesting thing then is we could control the indoor environment in a way where, for example, we can act on the air change. I mean, again, we had to study how the COVID virus thrives. Again, there are certain levels of humidity, temperature, so on and so forth, CO2 level where the virus can thrive and become dangerous. So we had to study do all the epidemiologist work, and as a result of that, we could control the BMS in a way that would minimize the risk of infections in the different spaces of the stadiums. So it was a very interesting work. We published a few papers that are available on my website if you want to consult these papers. But certainly that was a very useful exercise. The last thing I wanted to mention is in relation to the platform we've developed is, as I said before, we could trade at a space level. This is our building in Cardiff University. So we have a digital twin of the building in which we work. So again, it's a BIM model that we've augmented using Blender, so which gives a realistic view of the building. But certainly what we can do is very quickly move into a specific space. So we have either the IFC model of the space, or we can have this type of real-world kind of view of the space, but then we can interact with the objects inside of the space. For example, here we have a sensor. We have a sensor unit. So we can interrogate that particular object, the sensor unit, provide a time range between two dates, and then we can get all sorts of data about the temperature profiles, the level of humidity. We can get real-time data, and we can also predict what would be the indoor conditions of that space based on a number of parameters, such as the external weather, occupancy of the spaces, and so on and so forth. So again, we can also control indoor spaces, and in the same way as I mentioned before, we could optimize the different set points in a way that we turn the spaces as safe as possible from a COVID perspective, as well as reducing energy and carbon emissions. So this is the digital twinning exercise. The question is, you may ask, is so what? So the first thing that digital twins can do is to virtualize the sensing function. So we've done here a bit of calculation. If you take a sensing unit and you look at the life cycle impact of a sensing unit, which is around 11.6 tons of CO2 over 60 years lifespan. So if you multiply that by the number of sensing units you have in a building, office building or a whatever a public building, then this can really increase, that figure can increase dramatically. So the first thing we do with digital twins is virtualize the sensing function, and we have our approach of doing that. So that's the first advantage. When it comes to life cycle assessment, which I've mentioned to you before, using the same building as I showed you before, so using LCA open source tools such as Brightway 2 and using Energy Plus for energy modeling, so we can very quickly, again, we've done that through our platform, very quickly kind of understand or infer what are the impact categories, with the impact of the building across its life cycle, using a number of impact categories you can see on the top screen, right top screen. And then we can see clearly on the top that materials, hence my talk about materials, have the largest impact for a building from a life cycle perspective. So materials in green, you can see how across all the impact categories of the life cycle assessment, materials feature as the ones having the biggest impact on the carbon footprint of a building. Then if we look across materials here, in this diagram below, then you can see that in gray is concrete. So concrete, which, I mean, the building I showed you is made of concrete, reinforced concrete. So concrete before, because of the way concrete is being manufactured, processed, etc., features as having the highest impact from a carbon perspective across all the categories on the life cycle of the building. So you may say, okay, so what? I can get the similar thing with any LCA tool. Okay, fair enough, but the difference here is, using a digital twin, we can apply what I would call as dynamic life cycle assessment. So I can go deeper into my data, and here, what I've got here in the top diagram here, we can see over a year period. So we chose here 2020, during the period, the COVID pandemic. We can explore different scenarios. We've looked at 3 scenarios, which is in orange is the scenario that we used during COVID, and we were all working from home and in a hybrid form. Sorry, I repeat what I've said. In the orange, it's the business as usual scenario. Okay, so in blue is the scenario we had in COVID, during COVID, and in gray is an improved scenario where we went further than what most of us did within COVID, but try to turn off the heating in spaces that we felt were not occupied. So using dynamic LCA, again, thanks to a digital twin where we acquire live data on a continuous basis, can help us really have a fine-grained understanding of what's happening within the building. And if I go deeper into this, I mean, here you can see a peak in May, so I can go deeper and analyze that peak and understand over a 1 month period, look at the 3 different scenarios and understand really whether there are any trade-off possibilities to reduce my carbon footprint. So again, the reliance on the digital twin, the reliance on the data it provides, the different processes it can provide is quite interesting and offers a value added when it comes to managing the carbon footprint or life cycle impact of an asset. So I'm going to summarize what is a digital twin. So a digital twin can maintain a dynamic foreground inventory of a building from an electricity, heating and water perspective. It can provide more accurate estimates and time-differentiated results, which enable a more granular analysis of the impact of the way we interact and use a building. It can provide a fully fledged assessment of building energy and life cycle impact from an early design stage. You don't need to wait until the building is constructed to understand the impact of your building, and then you can start optioneering and looking at what-if scenarios which can impact on your design itself, initial design. You can, again, we're talking about BIM, so BIM takes lots of time, but using and can be expensive, time and costly. So using open solutions, open BIM solutions, so I think you can reduce the cost and time required to develop your BIM. And again, consultancies and practices can adopt this fairly quickly, again, thanks to the open BIM solutions that are available, as well as LCA and energy simulation tools. So, in summary, this is work we did for the Reading train station in the UK. We've been approached by Network Rail. They've asked us to really understand why the station is highly consumes lots of energy and carbon emissions. We've done lots of work, again, through digital twin, which we've calibrated, developed the simulation model. We disaggregated the data. They gave us data from the smart meter, so very limited data for over 5 years. We used that data, disaggregated the data. As a conclusion, we found out that the way the station is operated is completely different from the way it was meant to be operated. For example, lifts and escalators were working 24 hours a day, whereas during night time, from midnight until 5 o'clock, there was no train kind of passing by, so no passengers. And that really made them rethink the operational strategy of the station, which helped them then work on reducing their energy consumption and carbon emissions. So digital twin can help mimic the context and behavior of physical asset, as well as its parts. It can dynamically be updated with data that comes from the sensors and the information available about the building. And more importantly, it can inform decision making. So really, these are the added value of a digital twinning approach. Now, I'm going to touch on Germain's presentation. So really, for digital twins to be developed, we need the we need to have the right innovation ecosystem. So usually innovation is driven by industry practitioners, and we've seen the presentation this afternoon from the architectural practice and commercial innovators. We tend to deal with isolated initiatives, so we need really to have a more joint efforts between research and industry and academia also. And this is where we operate. We have an academic push versus industry pull. We need to put that in place, and that's something really we can deliver through having the right innovation ecosystem. So really what we need is digital twin requires a number of pillars, which are policy, science, industry, and society. So the four need to come together to deliver really the promises of a digital twin and scaling up this across the entire society. I will finish with the diagram, which really shows my reflections or summarizes what I've been mentioning so far. So the key words here with the challenge we face are sustainability, resilience, circularity, and life cycle assessment. These are the key themes that dominate or the key challenges we're facing right now. So we need to understand continuously the global challenges that we face. I did mention this earlier. So I think we have to ensure that our infrastructures are resilient all the time. Our cities are participative. I mean, we have climate change and so on and so forth. So we have the global and national challenges that need to be continuously understood. We need then to have a capability to translate these challenges or model these challenges using kind of the right tools. I mean, again, digital twinning is the approach that is probably the most appropriate. This should be applied not only for the built environment, but should be applied across a number of industrial sectors, energy and utilities, health and well-being, manufacturing, and so on and so forth. We need then to promote research and development. Again, I've identified here a number of cross-cutting research challenges: semantics, AI, information governance, privacy ethics, Internet of Everything, complexity theory, complex systems, and also the interaction between the human and the twin. So that's quite important. Human aspects are very important. And this is where probably Germain will talk about later. We need the right open innovation ecosystem, and this is really what is required to provide a platform to promote really the research that is needed to develop this vision of a digital twin across industries, as mentioned before. So by doing that, we continuously frame the challenges faced by sustainability, resilience, and so on and so forth, thanks to our capability of sensing continuously the challenges that we face, be able to explore digital twinning across domains, not only built environment, but across domains, and having an important route for open innovation. So I'm sure that Germain will expand on this shortly in his presentation. So that's conclude my presentation. Sorry for the long presentation, but I hope that I've managed to convey the key ideas that underpin the research that we do. Happy to take any questions.
I'll try to run as fast as I can. So anybody? Maybe I have a question. How do you see this technology used in the design, or how can we use it? And maybe even more, some states, I don't know how it's in the UK, in Slovakia it's not possible, but some states allow simulation to overcome the code. That if you have some code, but you prove simulation runs better with the space, for example, fire protection, it can be accepted, even though you don't respect the code which is like primary operation. So what are your experience from that, and how do you think we can use this simulation in design?
Yeah, that's a very good question. So the first question, you've asked two questions. The first one is whether it can be used for design. So the answer is definitely yes. I think when you start designing a building, so you start building up your BIM model, you start developing the, and this is where it becomes interesting, because I think I see the design process is an iterative and collaborative effort. So you want, in the early stages of design, you want all the stakeholders to have a say. For example, you may have a performance-driven brief where the architect may want a specific type of material with a specific type of performance, and so on and so forth. So it's very important to offer at the very early stage, and there are tools that do that, offer the architect the possibility of optioneering and looking at what are the options, what are the consequences of each option I take from a carbon perspective, from an energy performance perspective, as well as other aspects. There are tools that exist, okay? The problem that these tools may have is some of them are BIM compliant, others are not. Certainly BIM provides a way, the IFCs provide a way of bridging the gaps. You can move from one tool to another in a seamless way. But certainly, the technology I've been showing here requires a BIM. You need to have data about your building. And the ideal way to do it is to start the process of building your data from the early design stage. Okay? And the second question you said is about simulation, regulations, etc. So we do work with regulations. In fact, the approach we take, we semantize regulations. We'll be discussing this morning with one of the stakeholders we met. So we develop a semantic version of the regulations, and we can check using the IFCs whether the IFC data we have is compliant with the regulations. We turn the regulation into rules, and then this can be processed. As the designer progresses in his design, or her design, then we can flag whenever regulation. So we are progressing now an EU project called Accord, VTT at the coordinator, where we're putting this into place. So yeah, we have to comply with regulations. Regulations drive the design but certainly the solution I've showed you is something that is aimed at existing buildings, and we tend to operate during the operation stage of a building, which can last for decades, as you know. I don't know if I've answered your question. Thank you.
Thank you very much. You showed us very nice digital twin model of the city Cardiff. Is this model still in use for other projects than the station, or is it became a part of city development process, or is it just your initiative of the university in Cardiff?
Yeah, that's an extremely good question. So we've developed the facility for the Cardiff city, and really the issue we face with Cardiff is the issue of resources. I mean, councils in the UK are really, I mean, I don't know if you've heard about Birmingham City that have gone bankrupt. I don't know if you've seen that in the news, but Birmingham has gone bankrupt because, so the issue we faced is we delivered the solution, we gave it to them, but then they needed to deploy it on a cloud, they needed to have people who would operate it and maintain it on a regular basis. And yeah, so we're still talking to them and trying to help them with that. We did a similar thing in Luxembourg. Again, that was showcased a few years ago. But certainly where we do focus on is buildings. We focus on buildings because you have a client who's and with a building, you can convince a client and say, I can save you X% of your energy bill every month or every year by using this type of technology. So it's much easier to talk to client as opposed to be talking to a city, a wide city, where things are more complex, mainly from a governance perspective and from financial perspective. So certainly we've demonstrated it. It's a TRL 7. And now with the spin-out, we are transitioning to TRL 8 with the spin-out. But we have demonstrated it in the city, as I showed you here with Cardiff, and we did that with Belle Valley in Luxembourg.
And another more question. We also started with just small part of the city, and you already made the whole digital twin of all city. Did you start as well with smaller part, or you make the whole city at the first moment, and now you are making more detailed part to part of the model?
So what we did, we started with OpenStreetMap. We used an open source solution, so OpenStreetMap, but that was not complete. It was incomplete. But then there was a company, we've outsourced the massing of the city from a company that uses satellite data and then turns that into more accurate, with buildings with accurate footprint, etc. Once we've done that, we had to go and check building by building and check if the footprint was right, check whether the height of the building is correct. So yeah, I think it's a hybrid process where you have to acquire the data first, either from open source data such as GIS data exist, but then that is often not sufficient, or cadastral data that's often not 100% accurate. Hence why we have outsourced this work. I mean, the massing of the city was delivered by the third-party organization that uses satellite data and later technology to deliver what I showed you in the. So that's something that we don't do. But however, with the technology that we have, if you give me an IFC model or a BIM model, I can, if I know the geolocalization of the model, I can import it into the platform and position that where it should be positioned. And again, that can enable the participative approach where you can get citizens to look at, oh, this is how the building would look like. People can start providing feedback, making comments, etc. So yeah, we've got this capability. So as soon as we have an IFC model, we can import that into our urban fabric, for the landscape, and make that available as part of our digital twin. But if you don't have an IFC model, what you see is what you've seen before, like boxes representing the massing of each building. But our philosophy is if you build it, they will come. So if you have a platform, then give us your IFC models, we'll geolocalize, put them into the model, and they become part of the model. Yeah.
Okay, thank you. And is it the result is public free then? Everyone can see it and, for instance, rotate it or search it on the web page, or is it just when they will come, you will make this option for them?
So that's a very good question. It really depends on the governance approach in relation to the city or the building. Sometimes, if you could imagine, for security reasons, people may not want their building to be visible or accessible from third parties. But we will respond to the needs of the client. If people want everyone to see the model and interact with it, then we'll open it up. Again, we have a governance model. If you want to give certain rights to certain users on the model, again, because we have an IFC model, so we can control access to the different entities in the model. So yeah, I think it's something which needs to be configured based on the requirements from the client or the owner of the building. If it's a city, based on the city.
Yes, because here in Bratislava we had this problem a few years ago that just developers developed a certain part of the city and they presented only certain parts of the 3D model. Sure. And no one seen before the whole downtown or whole the city model at all. Okay. So people were surprised how the panorama city afterwards looks like. And that could be the problem. And now here they are thinking to make all visualization and 3D model publicly free before, just after improvement, to not be surprised when the building is done. So how it is in Cardiff?
In Cardiff, I think we have a planning authority, so you can consult any. There's a planning process, there's a planning website, so you can go and consult any. This is applicable mainly for the domestic sector, so it's publicly available. You can go and consult any house you want, and if drawings are available, you can download the drawings. But certainly, there's no BIM, so you have really drawings. That's what you have access to. The approach we're trying to push is to have BIMs or models available, because once you have the model, that gives you an incredible set of capabilities, really, to exploit that data and make good use of that data from different perspectives. So the tool I showed you is very open. I mean, if you have an IFC, I can, within 2 minutes, insert it in the model and it becomes a real building, as I showed you examples before. If I don't have an IFC model, then what we tend to do is just have the massing of the building. But then what we try and do is try and have at least access to the smart meter if we can. If we don't have access to the smart meter, then we can try to profile the building, and we have a way of doing that. I don't know if I have time. I can show you the 3 products that we have, but certainly, yeah, it's not a technical problem. It's more a problem of data availability. Technically, it's feasible, but the issue is whether you will have access, A, to the models that we need, B, to the data in relation to these buildings, because the difference is quite sizable. If you don't have a model, then the building becomes a node in a city landscape, and then the node, you try to have ideally data about the energy consumption and whatever is available. If it's a real building, then it becomes incredibly powerful. Then the model gives you a wide range of possibilities, really, to manage the building. And we're talking more and more now about the digital building logbook. The EU is pushing for every building, like a car, to have a digital building logbook. So I'm really very confident in the years to come. The buildings that we have, we need to have information about them, including the BIM. So that's a matter of a few years, really.
Okay, thank you. And my last question is about your students at the university. Are they interested in this digital twin model? Are they using it for their students' project to try and paste their design and compare it in this digital twin model, or is not available for them?
That's a very interesting question. That's why I asked the question earlier to the architects who was presenting, because I teach a AMENG module called Integrated Building Design. We give to the students to design a hospital, a 4,000 meter squared hospital in Cardiff. And the way they do is it's collaborative and iterative. So from the first time they start with a brief. We give them a brief. They have to interpret the brief. They have to turn that static brief into a performance-driven brief, so informed by regulations, etc. And then they use different tools. the Sapphira, there's a number of tools that can, at very early stage, establish the carbon footprint of your massing. So you start by massing first, it's a top-down approach. And then depending on the orientation you choose for your building, so they gradually move into, so they have one source of truth, which is an extended BIM. And they use a wide range of engineering analysis tools, such as Energy Plus. They use LCA tools. They use, for fire engineering, they use CFD sometimes, computational fluid dynamics, to look at the risk of fire. But what we try to push them to do is to move from designing a static building into designing a dynamic building that has a life cycle, and where the life cycle costing becomes important, because the capital costing is probably 1/100th of the final cost of the building. 99% of the cost is during the operational stage. So we're trying to encourage them to really kind of predict and profile the energy performance of the building and the carbon footprint, not looking at the building itself, but looking at its entire life cycle, which can last decades, even centuries for some buildings. The answer is yes, we do that, and we try to migrate from the BIM to the digital twin, because this is the future.
Okay, thank you very much.
Pleasure, thank you.
I had actually a question, but you touched it already. But I really find kind of intriguing that the programming and the social aspect of the building, how it's used, it's such an important part of the examination of this energetic part of the building. And it's kind of different approach even from the design point, because usually you just here add insulation or try to find some another sources of the energy from solar or whatever. But as you show, and that's a kind of question that in your experience, actually in a already built building or the old building, it's kind of similar problem here with this building. How or if you can say how much this energy could be really saved by just adjusting the program, and I think it's kind of smart building solution with the sensor and optimizing the energy consumption within such a kind of building like this.
Yeah, there are three factors that impact on energy consumption in buildings. The first one is the user behavior. So the way in which, as you've said, users interact with the building. That's the first aspect. The second one is the energy efficiency of the building from an envelope perspective. So again, the envelope has a key role to play. So that's the second point. And the third point is the way you operate your, you tend to have a BM, if it's a public building, you tend to have a building management system. You have energy systems that heat the building, light the building, etc. So the way you operate these systems. So these are the three factors that impact on energy consumption. So yeah, I think to answer your question, user behavior is extremely important, user behavior. And we've done lots of research on, when I say mining data, for me, a user is a sensor. A user, the way we've done lots of research on mining social media data, like Twitter data. And again, I can show you a paper where we looked at Cardiff. We tried to interpret all the tweets that have been generated over a certain period of time. And we really developed what we call the urban pulse of the city. So we could, only using the tweets, understand whenever, almost real time, when there's a crime, an accident, when there's a... so it was very impressive, and hence why Elon Musk has just, put Gork, the AI system that exploits his Twitter data. So we've done that a few years ago, and it was an incredible, interesting experience, because we don't need sensors. We only need to do sentiment analysis, understand what the users are saying at during a period of time, and that helped us really develop the urban pulse, so understand the urban pulse, almost real time of a city. So I want to insist really that social data is, and for me, users, the way we look at users now, we look at users as passive participants in an urban landscape. I think users should have an active role. Again, we all have a smartphone. We can all say, express our sentiments. And the systems we develop tend to be top-down and don't factor in the user feedback. So for me, any solution should have the user in the loop and should be participative. I don't know if I've answered your question, but
yes, thank you.
Yeah, pleasure. Okay, thank you very much. Thank you all.